Good. So it's my great pleasure to introduce our next CRM Applied Math Lab speaker, Professor Wolfgang Dahmen. He is a full professor at the Department of Mathematics of University of South Carolina, where he holds 2 chairs, a Smart State Endowed Chair in Data Analysis, Simulation, Imaging, and Visualization, and a Williams Hedberg Chair in Mathematics. And his research interests are really wide, crossing approximation theory, numerical analysis, computational harmonic analysis, learning theory, and he made really impactful contributions to, just to name a few fields, compressed sensing, numerical methods for PDEs, model order reduction methods. He has also, he's also the owner of numerous awards. I will only mention the 2019 Siam Fellow and the Gauss Lectureship in 2011, and also the Leibniz Prize in 2002. He also made outstanding service contributions as the chair of the Society of Foundations of Computational Mathematics. So Wolfgang, thank you very much for being here, for your time. He will be speaking from Germany today. We're really looking forward to your talk.
Thank you, Simon. I will get back to you for this long introduction. Okay, it's some time. Okay, so it's my pleasure to meet you, at least virtually. So as you are going to see in my title, you see that word thoughts. And this is in fact what I'm going to do, to present some thoughts. And it will and on a topic that is very hypey. I mean, deep learning, in particular PINNs, it's an acronym everybody knows, probably physics-informed neural networks. It's very much under discussion. But maybe unlike most of the talks on this subject, I'm not going to flood you with pictures or tables. I'm actually flooding you with some thoughts. So let's see how this is going to work. Here is a rough overview of what I'm going to talk about. So first, I will explain my core interest in the problem type. And then there will be a theoretical foundation part, which is the section 2. And then there will be, based on this, there will be some thoughts about possible numerical realizations. And you will see that there are some issues that are maybe less pleasant as than the hype really claims. So what is this about? To put you in the right framework, I think it's good to look at 2 cartoons. These are almost the only pictures. So a classical problem is porous media flow, where you have only a few measurements, like maybe I can activate. How do I activate now my panel? Okay. So you have these few measurements here, which give you the pressure heads. What you really would like to know is the structure underneath your feet, which you can't see, which you only can sense through a couple of measurements. In a very similar, seemingly different, but very similar problem is what's called electron impedance tomography. It's a very bad, ill-posed inverse problem. So you would like to see what's going on in your body, and you only have some electrodes wrapped around it. There are only finally many of them, so you can't put too many boreholes on this side, and you can't put too many electrons around you. And from some probing, by sending some current into your body and measuring the voltage of the response, you try to infer on what's happening inside. So in both cases, let me put this away. In both cases, the mathematical model in the simplest form, and it's only for a matter of principle, is a family of PDEs. I will always write it in this kind of residual way, that I'm looking for finding a zero of an operator equation. So I'm always looking at the residual. And in this case, the residual is just a second order diffusion equation, the Poisson equation, where now the variability of the model is sitting in this diffusion coefficient, which could be permeability on the left side, and conductivity on the right side. So it's essentially about finding what specific parameters are behind your measurements to explain them. But the point is that all viable states are described by this PDE when Y traverses a parameter domain, which you could view as a design space, say. So what you're interested in is this geometric object, which one sometimes refers to as the solution manifold. Namely, these are all the states which you obtain when Y marches through some parameter domain, which, and this is one of the challenges, will typically be very high dimensional. So as soon as you ask for accuracy in terms of the underlying continuous model, you have to decide where your objects which you want to approximate are living. So you have to decide on a space U, and this will be consistently denoted by this U, which is the space that hosts all these states of interest, the U of Y, the points in the solution manifold, where each point is a function living in a particular Hilbert space dictated by the PDE. In this case, it's this space, okay, or some close relatives in terms of different boundary conditions or things like this. So that's the setting. So that's the center of interest, the solution manifold. Given the fact that the states which make it up depend on possibly many parameters, so that they become as functions of X and functions of Y, they become functions of many variables. So if we kind of wrap this up on an abstract level, this problem setting can be described by this. We have a physical model, a background model. It's a family of PDEs depending on a parameter that may vary over a high dimensional domain. And the states of interest are collected in that solution manifold, which we had introduced before. So these are just the solutions of the PDEs when you vary the parameters. And why are we interested in this? Okay, exploration of M means you really explore the design space and can see what these states really give you in information, but more importantly, perhaps inverse tasks, like you are given these finitely many, typically very few measurements from which you would like to identify a state behind these measurements, or if you go even further, which is more difficult, find a parameter that explains these measurements best. And this is typically deeply ill-posed because there are typically even more than one state that explains what you are seeing. But that's another problem. So that's basically the issue you would like to explore. And at the core of it, from a mathematical perspective, is one needs to understand this mapping that takes you from any of those parameters to the state, which solves the PDE for that particular parameter. We call it the parameter to solution map. And the talk is about a recent interest, a growing interest in learning such parameter to solution maps, which are therefore basically the key to your model understanding, to learn them in an efficient way and hopefully even parameterize that mapping in a way that it can cope with the high dimensionality. In other words, that this is a representation that is not subject to the curse of dimensionality. That's the core problem. But always with an eye on the question, whatever I do now in terms of model reduction with this, what can I say in the end? How can I certify the result I obtained in a numerical way? Okay, before we go into that, let me just hit on the two ways to view the states. One way is we look at this parameter to solution map, and that identifies a point in a Hilbert space, which we call consistently U. which, as I indicated before, is dictated by the PDE. In that simple model, it was just H10. There is another way to view it, namely, each state u of y is a function in x. So you could view u as a function of x and y. And then it lives in a function space, which we call x. And that function space is now concerned with elements that depend on many variables. So that's a high dimensional function space. U is just a function space of typically 3 variables, maybe 4 if you have a time variable in it, which is it's covered by what we are talking about. So the first question when you asked for pinning down the quality of such an approximation to the parameter to solution map is you need to fix the metric in this setting. All right. So how are we going to do that? As I mentioned before, most interest is in learning this parameter to solution map. And here is our favorite hypothesis class, deep neural networks. All I want to say about this is I don't give you any technical discussion of it. What matters is there are combinations. There are combinations of very simply parameterized mappings acting on typically high dimensions. So we are looking for a surrogate that explains the states of interest as a neural network so that whenever we want to evaluate that parameter to solution map, we just have to evaluate in the end a trained neural network. And I will consistently denote the hyperparameters or the trainable parameters by theta. Okay, so what does learning mean? Well, learning means the most natural thing now to do is that we try to minimize an expectation. And this is this part here. An expectation now over the deviation of the true state and the surrogate, which I hopefully will train well enough. But that deviation lives in the right topology, which is compliant with the model, which is the norm in U. And the expectation is over the parameter domain. So implicitly, we make a decision. We treat everything spatial deterministically and everything in the parameter domain stochastically. And there's a good reason. There has been quite some work about reduced models based on reduced bases. And that has been very successful for certain types of problems. Roughly speaking, problems where the parameter to solution map is very smooth. But to train a reduced basis in a rigorous way requires monitoring errors in L infinity, in particular in L infinity over high dimensional parameter domain. And that's fully subject to the curse of dimensionality. If you want to have a rigorous result, you would need coverings with a certain accuracy to train on, and that is fully subject to the curse of dimensionality. So instead, by going to such an L2 setting, like here, you have maybe a better chance. You get a weaker result, a weaker accuracy quantification, but you have a better chance to cope with high dimensions because you can rely to some extent on Monte Carlo rates. On a smaller scale, there will be, of course, other problems, but this is the setting I would like to focus on. So ideally, of course, this expectation is nothing but this Bochner norm. So ideally, we would like to train the networks to approximate well this Bochner norm, where the spatial part lives in a Hilbert space, which is not just L2, but typically H1 or something else. In transport problems, could be more nasty and more complicated, but this is what it is. So our interest is to understand this mapping quantified with quantified accuracy in this metric. All right, so what do people do? Well, the most natural thing is to minimize an empirical risk. There is this continuous L2 functional. And for the moment, people ignore you and the Hilbert space. They just sample the solution at points in the domain. So these are points in the domain. And these are points in the parameter domain. okay? And then you'll set up this mean square functional, and you try to find a parameter that defines a network which minimizes this distance. Well, after all this introduction before, this is not the most clever way because it's not the right norm. And if you're interested in controlling fluxes, this is certainly not the right norm for a second order problem. But in essence, that can be switched by still extending your purely data-driven approach to mean square risks, which are now, with regard to the spatial part, put in the right space, but where you still do an empirical risk over the parameter space. And this has been done in a number of papers. I mentioned a couple of authors down here at the bottom with impressive results in terms of the scope of problems and in terms of the difficulty of the underlying problems. What is difficult to say, however, is how accurate are the solutions? I mean, how do you evaluate that? Maybe you can do that by first inserting a ground truth, which necessarily is always simpler and more benign and smooth, but it's very different to really assess the accuracy of such an approach in a realistic scenario. Something similar we did, I did with Zhu Wang and Min Wang, not for learning the parameter to solution map, but directly a data to state map, which but uses the same principle of, however, using the right metric. So in other words, respecting the right metric in the spatial domain, but relying on these snapshots. And this is the little wrinkle with this approach, and we realized we pay for this. Namely, in order to get acceptable accuracy through such a learning approach, you need many samples. And each sample is a high fidelity solve of the PDE. And that's very expensive if the number of parameter samples gets large. And if the parameter domain is large, you may need many samples to get an acceptable accuracy, or you are satisfied with something crude which you don't really control. So there's an issue which made people look at an alternative. And that alternative is that famous PINN, physics-informed neural networks. The basic idea is very simple, and it has been used in many other contexts before. The construction of reduced bases is based on the very same idea, namely that you minimize something over or optimize over residuals. And the idea is very simple. The solution U would make the residual to 0. This would be the ideal solution. So the rationale is then, as long as I make the residual small, I'm in good shape. I have something close to the real solution. So instead of training on snapshots, which are expensive to compute, you just stick an ansatz, your neural network, into residual, and then try to minimize this. Okay, so that looks like that. So you put your neural network into the residual, and then you train over those hyperparameters data and hope that it does a good job. At the moment you are generous, and there's a lot of papers doing this, and maybe those who have introduced it, big work has been done by George Kaniadakis, Raisi, Mishra has been working on this with various co-authors lately. So it's a very vibrant development. So, and essentially this is what they do. They take the residual, evaluate it at spatial variables and as parametric variables, and then use and then optimize. And there is a very tempting aspect to it, namely, this fits very well with the neural network backpropagation framework, because it resides on evaluating these objects and doing very quick gradient computation. So it has a big practical appeal. I wouldn't be talking if there wasn't this slide coming, namely that there is an issue. And it suffices to look at a very simple example to see that issue very, very clearly. So let's go back to our old fruit fly, namely the second order elliptic parametric problem, which we discussed at the very beginning. So the relevant Hilbert space U is now H1. And if you fix zero boundary conditions, H1, 0, otherwise there could be variants of it. And if you do that same recipe, this is what we get. So the residual risk, that empirical risk now, has two parts. Namely, it has the bulk residual, where we stick the neural network into the Laplacian. This is this. And then, of course, we have to fix the boundary values, because neural networks don't do that voluntarily. You have to force them. And here is the way it does. It's done again in a mean square sense. So we evaluate on the boundary. These are training data on the boundary, and minimize that object to drive it to 0, say. Okay. So now, of course, you would say, if I let my samples go to infinity, I should get very accurate results, right? The more samples I have, the more tighter will my training result be, okay? Let these samples, xi and yj, let the number go to infinity. So nx and ny go to infinity. What will you get? Well, the first part gets you this residual in L2. The second part gets you the boundary residual in L2. And whoever has taken a first course on PDEs knows, now I gotta be careful, because why is that? Does this actually relate to my norm? Remember, the original goal was to minimize this one, to find a solution in this norm, because it means you control deflections and fluxes. And the fluxes are in many applications more important than the deflections. All right. So is that possible by doing this? Or would, whenever you stop the training, would your object E of theta, would that convey any information about this error? I would say there's a big question mark. And why is this? Because it's not variationally correct. This term is definitely too strong, because you need full elliptic regularity in order to make your residual live in L2. Of course, the neural networks do. You can choose them smooth, but the limit doesn't necessarily. If you have piecewise constant coefficients, which in many models is the case, this residual definitely doesn't exist. So when you train on it, you build in an instability. You make an ill-posed estimation problem, potentially even more ill-posed. The second term is always wrong, because traces don't live. They live in L2, but they actually live in a smaller space, which is H1/2. So this part of the second part of this training risk is too weak, and the first part is too strong. And therefore, I claim it's difficult to infer on this quantity. Anyway, I had a recent paper with Rob Stevenson and Jan Westerdiep on a related issue, namely data assimilation in parabolic problems. So that was a space-time problem, where in the space-time cylinder, on a subdomain of the space-time cylinder, you get data of the solution. It's an ill-posed problem. And here we made a point to train the estimates on the variationally correct risk. And it turned out, after some discussion with hardcore representatives of this area in mathematics, there's a distinct difference. Namely, the prior work on similar problems was different in that they use training risks that are stronger, which from the very beginning impose excess regularity. And they're only valid, the results are only valid under excess regularity. It turns out that your estimates you can only get if you assume consistent data, which is never the case in practice, and that your estimates remain dependent on a regularization parameter, while ours don't. We get a posteriori estimates that are rigorous, and we get a very good consequence on the solver side, while they cannot quantify any kind of computational complexity. So it made a huge difference to employ the variationally correct numerical risk. So this is one of my points. So the real spaces in which, or the real norms in which you should train the residuals on is this weaker space, where instead of L2, you have H minus a half. And on the boundary, instead of L2, you should H a half. That would be the variationally correct list. Of course, you see immediately what it means. I mean, these risks are much harder to evaluate. They are not as easy to evaluate. And that's one of the big troubles, in my opinion. Of course, it all doesn't surface too much. If you have a very benign example, you apply it to. If you have more than H2 regularity, of course, it does the right thing in that. But I would say not in general. So here we are going back to the thoughts now. So what to make of it? So the question is really, can you have any prediction capability without accuracy assessment? And you have to make up your mind in which sense. I would put a question mark there. And then there's another question, which in my opinion distinguishes the whole field very much from the classical scenario. In the classical numerical analysis world, we got very far by having good a priori estimates in conjunction with, say, regularity theory for PDEs. They predicted very accurately what you can expect, and they give you a very good clue of what the order of magnitude of your discretization should be. Of course, a posteriori error is even better. They could steer adaptivity, and they could even pave the way to more complex problems. Fine, but already a priori analysis gets you quite far. And since the algorithms are well understood and they give you what you want, there's no risk in your algorithm execution. So this is a completely different scenario, because now with neural networks it's different. You have a significant training uncertainty. You don't know whether you reach any reasonable optimality, what the expressive power in theory could provide. And there are interesting discussions by Ben Adcock and Nick Dexter, and later in a paper by Gross and Vogtlander about this theory to practice gap, even showing that under certain circumstances you cannot realize a theoretically possible high approximation rate. So what is then an a priori estimate buying you? What is the expressive power telling you? Not so much, I claim. So on the contrary, when you stop your optimization, you would like to know how accurate you are. So in reality, you need an a posteriori estimate that allows you to evaluate a quantity, which then gives you a rigorous information about your accuracy in a problem relevant norm, not in some metric, in a problem relevant norm. That would be my ideal. Okay, so everybody needs a goal. So that is this discussion. Then of course, it comes with avoiding excess regularity. In my opinion, one shouldn't formulate a scheme which from the start requires some regularity which is not in the intrinsic setting, but which depends on additional knowledge. So I think this is and this showed very much in this paper. There it was a significant point. And finally, you have to deal with this high parameter dimensionality, and then in the end, do we have to reinvent the wheel for each problem, or is there an underlying general mechanism one could execute? So that's what the rest of the talk is now about, with these few intermediate thoughts. So now we get to the heart of the matter, what I call variationally correct residual risk. So let's get back. So the state we are interested in is this mysterious U. This actually is a function of X and Y, but for each individual Y, it solves a PDE. This is this. But it's really a function that lives on a high dimensional space. Just this. Okay, I say the key to understanding this properly is to first understand the weak formulation. So we have a family of variation problems. by taking that residual and viewing it as a functional that you apply to a test function, which in our classical way means we multiply the PDE by a test function, and then we do something like integration by parts, and then we see what we get. Usually we get some smaller constraints on the regularity of the input. Of course, that happens. So now we get a family of PDEs, and now I'm not insisting on elasticity, not insisting on coercivity. That means my test space may be different from my trial space. And in fact, if I insist on stability in a strong sense, in many cases, it has to be different from my trial space. Otherwise, I cannot get stability in a way I explain in a minute. So here's this other object, V, for test space coming into play, which in some sense should relate to this U, which is the trial space, for the spatial part of the problem. All right, so next step. But we would like to see that U as a function of X and Y solves an operator equation so that I can formulate a residual which I can then train on. So what is this residual looking like? Well, I integrate over the parameter domain, and now my test space is the old one, but integrated with respect to the parameter domain. So that's now the natural test setting. This will be my space Y, which will fit to the space X in what follows. So now I have a variational problem on these high dimension spaces. And now I can abbreviate this, and I have a residual on U as a function of X and Y. And it is tested by functions V of X and Y because they are sitting, not in this one, sorry. Not in this one. They are sitting in this one, in this test space. Now, what that means is such a variational formulation. This is my my bilinear form in the high dimensional case. It induces an operator, which I call B, and that takes X into Y prime, because I'm testing with guys in Y. So that has to be, that should be a bounded linear function. Okay. Now, what is nice is because I'm L2 in the parameter domain, which is self-dual, going to the dual space doesn't affect the parameters. It just affects the spatial part. That helps a little bit, makes things easier in a minute. And then I can tell you what exactly gives me a sound theoretical foundation for a residual risk that is equivalent to errors in the problem compliant norm. So, well, it's almost inflated if I call it the theorem, but here is what I have to say, what I want to say. So I take any guy in X, which is not my desired state, and I wonder how far does it deviate from U? And it does deviate from U controlled by a quantity which is uniform. Let's see, lower and upper bound. Well, because U minus W is a lower and upper bound, this other thing is a lower and upper bound too. Namely the residual. So it is possible to express errors in my relevant metric, which is X, which has the spatial part U, by a residual which now lives in Y prime, which is the wrinkle, as we will see in a minute. Well, this is not for free. I cannot get this for any old choice of Y. I can get it only for specific choices. And these specific choices are exactly determined by what's called the Babushka-Neches theorem. It says, this error residual relation or tight error residual relation, this is the acronym for this one, this is valid if and only if X and Y are a stable pair for the bilinear form here. And this stable pair is determined by the validity of these familiar conditions. Namely, the bilinear form should be continuous, and the bilinear form should satisfy an in-soup condition, which means the operator B is injective. This means the operator B is bounded, and this means the operator B is injective. And this third condition, which is an in soup condition like this, only with the two spaces swapped, by the way, that should be an X here, that's wrong, is a surjectivity condition. So that's the famous Babushka-Netsch's theorem. And why does this say errors in X are equivalent to residuals in Y prime? Because these conditions are simply equivalent to saying that operator B is an isomorphism. So if B is an isomorphism, the observation is that a residual, let me say this. So this is really, oops, this is really F of W, that's the residual, sorry. That's the residual. Go back to my marker. So that this can be written as B times U minus W because F is BU. And because B is an isomorphism, that means the Y prime norm is equivalent to the X norm. And this is what we wanted. All right. Now we have this high dimensional variational problem. When is this in soup stable? Well, the simplest answer is, and that's not a necessary condition, but the simplest sufficient condition, if my individual choices of trial and test space for each Y, if they are stable pairs, in other words, if in soup conditions hold uniformly for each parameter dependent fiber problem, then the parametric lift of this operator or this bilinear form is in soup stable too. So in other words, I'm back to my old bread and butter, namely understanding a PDE for each parameter. And if this is in soup stable, then I'm in business. Okay, this is a nice theoretical framework. It extends a couple of things that have been done in the literature, but of course, so far it's only theory. And we'll see that this has a number of wrinkles for sure. So, but before we do that, let me hit on a few examples. I mean, there's a wide scope of problems that's covered. So coercive problems trivially, but saddle point problems if you satisfy the LBB condition. A lot of space-time weak formulations, parabolic wave equations, Schrödinger equations, even pure transportic problems like radiative transfers or some kinetic models can be covered by this setting. So it's a wide, interesting scope. We go by the same paradigm. And here are some authors that have worked in this direction for the radiative transfer. Me as well, will maybe come later. And transport is a keyword. Let me take this because it also highlights some benefits, but also some difficulties. So here is a transport equation, a parametric transport equation with the nasty parameter dependence, namely the convection field depends on the parameter. So each time you change Y, you have a transport in a different direction. Now you can only impose inflow boundary conditions, that is, and those parts of the boundary where the convection points into the domain, that's clear, to make it a well-posed problem. And then you have actually several options for a weak formulation. As I pointed out before, the weak formulation is the key. The first option is, well, you say, I look for solutions for which these directional derivatives are in L2, and then you can test with any L2 function. This is this case. So the trial space is the graph space with these directional derivatives, or family of graph spaces, and the test space is L2. You may not like it because if you change the Y, the direction changes and the sets even change. So all of a sudden, the solution manifold doesn't make sense anymore because for each Y, you are in a different space. So there's a second option, namely you do integration by parts and move all the derivatives to the test side. This is what you get here. But of course, then you get a boundary term due to integration by parts or Green's identities. But you free the solution from derivatives, so now your solution may live in L2. Now the test functions depend on the parameters, but that's not so bad as the trial functions, I would claim. So in this case, the trial space is just L2. And the test space is now a graph space type object. It consists of all these functions which now vanish on the outflow boundary. So that leaves you just with the data on the inflow boundary. So this is just data. And otherwise have these directional derivatives in L2. Notice the interesting thing is here now boundary conditions become natural boundary conditions because they become part of the function. That means in a least squares, if you train on a risk, basically you don't have to implement explicitly these boundary conditions anymore. They become natural boundary conditions. Whether a training of networks is strong enough to realize this is another issue. But in principle, this is what you get. So you get a certain relief with respect to boundary conditions. So is there generally a recipe? I say yes, in principle it is, and it's well known in the DPG community, by the way, and it works like that. So you look at your operator, or whether it is from our particular setting before or general linear operator, you ask yourself on a sufficiently dense but smooth set of functions, is it actually a bijection, or is B star an injection, the dual operator? If it is, then this defines a norm, because B goes from let me do this maybe. So B, remember, goes from X to Y prime, and B star goes from Y to X prime, or from U to V prime and from V to U prime. This is why there's a U prime here. But if you make this a norm, if you define your test norm zone, and that's in this way, and that's usually termed the optimal test norm, then your in soup constant is 1. In other words, you get an isometry. In other words, residuals in this metric are equal to errors in your metric you are really interested in. So the choice of the test space becomes a tool. And when you say, well, that norm I can't evaluate because I already have a dual norm here, and dual norms are nasty because they involve a superimization. But if U is actually, oh, that was the wrong button. Here. If U is actually self-dual, in other words, if it's an L2 space, then this becomes absolutely accessible. When is U an L2 space? This is what's called an ultra-weak formulation. And an ultra-weak formulation was what I did before with the transport equation, because I moved the first order derivative to the test side. Do I lose much in this? Answer is no. If I first, and that's sort of the recipe, and this is being used in the DPG community a lot, if you first write the PDE, if it is not first order, if you first write it as a system of first order equations through a mixed formulation, and then you move all derivatives to the test side, boundary conditions become natural, then you arrive at a situation where you can compute this. And you can work with it, let's put it this way. And it puts you into this favorable, very stable situation. So that's basically the philosophy here. If you do that to a second order problem, you first write it in a mixed formulation, you can do this ultra-weak formulation, and now you control the deflections in L2 and the fluxes in L2. The fluxes are still in L2. So you still get a control on the first order derivatives. So you don't lose everything, although it's called ultra-weak formulation. And this has been done in a number of works. By the way, this was used in the double greedy reduced basis method in exactly the same fashion, exactly the same idea. That give you Kolmogorov conforming reduced basis in non-elliptic scenarios. Well, that was the theory. Now, what is the practice? Now you have to compute. Actually, you want to train on these guys. You want to train on these fellows here. And that's not so completely trivial because it's a dual norm. So let's see what it means. So what we have done is we have, and that's generally the objective, we have turned the PDE into an optimization problem. And we have turned it into an optimization problem in such a way that the objective function is directly equivalent to the accuracy we are interested in, namely in the norm X or in the norm U for each Y. But there's a price for it, as you see, because we would like, and first I want to say is driving this residual to zero is equivalent to solving my original lifted variational problem. It's the same, it's equivalent. So minimizing this residual would give me a quantity which, when I stop, would tell me the size of the error. The problem is, the price is, this is a dual norm. And the dual norm is defined through a supremization. So this can be formulated as minimizing over U or W here as a candidate, but at the same time we have to supremize over the test side, because that is exactly this dual norm. So that's a min-max optimization problem, and people have used this. There's an interesting paper on the elliptic problems by Bao and co-workers, and also by these 3 or 4 gentlemen on so-called Friedrich systems, which is a class of PDEs formulated already in first order, for which one has an equivalence like that of a dual residual to the error in the norm you have chosen before. So for special cases, this has been addressed, and this is theoretically, as I said, because it's my own, I have the same point of view, but actually this is not so trivial to actually solve. So I'm not going to show you numerical results, but it's a delicate problem, and you may understand why in a minute. So how to do that? So in other words, we have to solve a min-max optimization problem if we go this way. Now, given a hypothesis class, say consisting of neural networks or tensors or whatever you want. So the idea would be to approximate the solution over this hypothesis class. You would have to minimize this object over this hypothesis class. Now, that means for each candidate, you ideally have to find the supremizer, which does this here. But that's, of course, completely impossible. But a closer look says, well, you don't really have to find the supremizer. You have to approximate the supremizer. So, and here's a quantification of it. If you are able to approximate the supremizer well enough so that this is lower bounded by the true dual norm, then this is, of course, absolutely sufficient. Notice that this is always upper bounded by the true dual norm, because that's, oops. This is the disadvantage of this path, this tool. Oops. Here. Yeah, because this is, of course, the supremum over all those tests that give you the true dual norm. The issue is you need to bound it from below by the true dual norm. In other words, that object has to be close enough to the real supremizer. But if you manage to get this lower bound, then of course you have a tight error residual relationship. Then this object will be a residual which you can train on. Each time, of course, adjusting also the V star. But this is then equivalent to your error of interest. So that's the guiding point. Well, How do we know what is close enough, and how could we get to it? Well, there's a simple observation. First of all, these supermisors can be interpreted in a different way. Namely, the supermisor, the exact one, is characterized as a solution of a variational problem. Namely, it solves this variational problem, where this is the scalar product in Y. So this is an elliptic problem because it's a scalar product there. It's bilinear, symmetric, so it's elliptic. Here is the right-hand side is a functional, which by definition lives in the right space. So that object is called the Riesz lift. It's an isometry because the coercivity and continuity constant for this elliptic problem are 1, because we are using the same Hilbert space inner product here. So this is actually a solution of a variational problem which is very friendly. And as such, you can characterize it as a minimizer of an energy. And that's a simple quadratic and the simplest quadratic energy that you can have. And you can get some mileage out of this. I'm not going into this detail. What it means to be close enough. Roughly speaking, it means you have to be close enough in relative terms. In other words, we have to find a guy which approximates the Riesz lift in relative terms well enough. So A should be less than 1. So this should be less than 1. And as soon as you manage to do that, you are in business, and you can go this route with the min-max problem and can expect even some rigorous error estimates from this. But you can already see that this is a delicate issue. And these are the two avenues. And I can see I'm only going to discuss one of them. I hope you bear with me for another 5 minutes or so. The first avenue is what's more familiar to people in the neural network business. It's related to GAN, which is a high-P object in the deep learning community. It says Generative Adversarial Networks. And the idea is very simple. In order to solve my, oops, yeah, I already done it. So you have to min in some hypothesis class, but then soup over V and the whole Hilbert space, f of WV divided by V. What you do is you discretize both. You discretize the W by a neural network, which is called the generative network. Oops. This is this fellow. And then it's challenged by the adversarial network or the discriminator, which is this. So this fellow, this one is to approximate that supermisor here. And that's essentially already the big wrinkle you see. Namely, if you choose, for instance, a parameter budget for your discriminator, which is not rich enough, you may never be able to come close enough to the true supermisor. If you don't get close enough to the true supermisor, you are training your network on a wrong object, not on the norm you would like to train it on. And you can see that in experiments very clearly. So the delicate part is actually to train the discriminator very well, because if this is too far away from your true supermisor in terms of this relative accuracy, which I explained in the lemma before, you won't train in the right direction. So it's a delicate problem, and these basically the results of these people reflected. So essentially, it's difficult to get very high accuracy in this case. So the second thing is which I call a hybrid strategy. It taps right into DPG quasi-interpolance. It's an optimization method where I would regularize the network by staying close to a piecewise polynomial as a function of x, very roughly speaking, and then use the fact that DPG methods give me a rigorous error indicator, which I can use in this, and that avoids the GAN altogether. So I don't have to use, I don't have to solve a min-max problem, but just a minimization problem. So I won't have time to this, but I may give you a few remarks on that first. GAN approach. Okay, the first thing what I guess many others do, and what we did at the very beginning too, we just take this quotient, where we have to take the supermization here and do an alternating optimization. So we do a few steps in gradient ascent of this quotient, and then we do a gradient descent, and then we iterate, and we hope that things converge to the right thing. It generally doesn't, but of course you have instances where it does. But so we started to think about alternatives, and I give you the very simplest way. There are other more elaborate ones which I could not explain here in a couple of minutes, but here's a simple way. So this in min-sup problem is equivalent to minimizing this quadratic convex benign wonderful functional over the pair W and V, but subject to a condition. And that condition is that V is the Rees lift. In other words, the supremizer. Because then I'm actually minimizing the right objective. So this is an equivalent thing. This, in turn, I can write in a Lagrangian formulation. So the primal problem would be to minimize over W and V, and then supremize over Z, which is the Lagrange multiplier. And then it's not very difficult to determine the dual problem of this, which consists in swapping the inf and sup. So you first execute the minimization over W and V, and you see the V minimization doesn't even see the first term, so it goes right into here. And then you see that's the old familiar energy minimization, essentially. And what you end up with is the dual objective is the minimization of this quantity. And then you can use the fact that the duality gap here is 0. So you can instead maximize the dual objective. But maximizing the dual objective now becomes minimizing the energy, because you just swap the sign, and you are back to an energy minimization. So this is what we are currently doing. It sort of does work, but it needs a lot of additional tweaks which we are exploring, so I don't give you any of this. Here's a typical idealized scheme. I'm always guided a little bit by my early experience on adaptive methods, in particular for wavelets. The essence of this was you view the adaptive method as an idealized iteration scheme in infinite dimensions, and then you understand this scheme, its convergence properties, and then you realize each step within a target accuracy, which is dynamically updated, and then you can show optimal convergence. The same here. So I think it helps doing first the minimization over the full Hilbert space, and then see what it takes to do the intermediate steps in an approximate way. That's the philosophy. And if you do that in an infinite dimension, it's actually easy, because they are nice convex functions. It's nothing difficult on the infinite dimension setting. It only gets difficult because you decided at some point to stick a highly nonlinear object into a very simple objective function. And that makes it difficult, because that screws up convexity all over the place, and you end up with all these pitfalls that force you to do gradient, your stochastic optimization tools and things like this. But again, as a side remark, in the ultra weak formulation, you can actually one direction, the descent on W, you can actually do analytically, and then it boils down to training something you have computed. So you could pull out an order encoder to do this. And the descent, or the gradient S on the Lagrange multiplier, is nothing but a descent on the energy function. So this is one way to do. But in practice, there's a lot more to do. And I think I'm already over time. Let me give some thoughts. We are back to the thought place. So what we have seen already is the adversarial network has to be close to a reflex of the current residual. And this may not be possible if you have the wrong budget, parameter budget for your discriminator. So I don't see any way to get to really rigorous results anyway beyond making a network adaptation. In other words, leave the flexibility to adapt your network in this whole iteration. So what we have not done yet properly is to do these steps in a nested iteration format, to start with a very coarse budget on the primal side, then do a lot of effort to determine a good supremiser on the dual side, and then pull it out. And then, of course, the supremiser will stay close. You will never explore the full Hilbert space, which is anyway impossible. So these are natural things, but they cannot be done if you don't have a good way of expanding networks and controlling them. So the other direction is that these functionals are really originally very benign. They are posed on the Hilbert space, they are quadratic or affine. So what could be better? So it invites you to look at an attempt to realize natural gradient flows. This is a current ongoing work with two of my colleagues at Columbia. And it's not quite ready to talk about, but I think it's a promising direction, because in the Hilbert space, you would know what happens when you can execute a natural gradient flow in say generated by this energy. And so this back to my original wavelet thinking, that I'm trying to do this in infinite dimensions and then see how close can I get in an instance of an execution for a specific parameter budget, or how to increase the parameter budget to stay close to that natural gradient flow. But as I said, it's not really enough. But if you do that, if you do adapt the network in a certain sense, expanding it, making by at the same time increasing accuracy, you see big differences here. Without going too much detail, this from this other work where we trained data to state map directly. So you see, this is when the network is being expanded using ResNet structures, as opposed to the standard procedure of just using stochastic gradient descent in all sorts of variations with changing learning rates and things like this. So in all cases, this kind of expansion strategy actually did better and was much cheaper, because in the ResNet structure, you can only treat, you get away by treating always the last block, by optimizing the last block, if you are careful enough with the previous ones. Anyway. All right, I skipped this because there's not time to go to this DPG kind of hybrid approach, which I think is quite interesting. And there's this last section, no free lunch. And the question is it worth the effort? Well, I don't know. It's more on the philosophical side. I mean, the whole PINN starts out with being very practically friendly. So you can give it to an almost uneducated person who knows how to run PyTorch, and you formulate your residual, and then you run your software. So this is a big plus in a practical application. Only my reservation is if you don't know what you get, then I don't know what the big plus is. But and for sure, for certain problems, this actually works. But in general, I have it. Then by the very nature of what we did is this training these residual-based risks avoids computing any snapshots. So you don't need an additional solver that gives you snapshot solutions. So you could use that as a method to solve the PDE itself. Just forget about the parameters. That summation over the parameters is gone. You have a deterministic solver for the PDE where just training the residual. I have not seen an instance where this can compete with a good established method. Not in complexity, not in accuracy, not in reliability. However, a potential advantage would be you can apply it to many different problems without each time becoming an expert on that particular PDE. So again, it's weighing certain aspects on a practical level. In terms of reliability and accuracy and performance, I think it can compete. But in these other respects, maybe interesting. So when should it be applied? Well, if your solution, I mean, this is different from using it as a model reduction. When I try to learn this parameter to solution map, this is really a model reduction. Then the difficulty is in the high dimensional parameter domain, and there it may pay a lot, as opposed to just solving a low dimensional PDE. But even in the high dimensional regime, if the so-called Kolmogorov widths, which are a measure for being able to approximate the solution manifold from a linear space very well, if they decay quickly, I don't think it can compete very well. So this is not the regime, but there is another regime. And I come back to my parametric transport problems. And I have a paper in preparation, which I think I can show that now you can train a network, or there is a network that approximates the parameter to solution map to accuracy epsilon, which is not subject to the curse. So even for high parameter dimensionality, because the parameter dimensionality goes only polynomial. Dx is the spatial dimensionality. So it goes in polynomially and maybe in that log. But otherwise, you get a low dimensional influence of your spatial dimension on the budget of parameters which you have to invest. But I have to double check whether I made a wishful thinking mistake. And that's it. Thank you. I think I imposed on your patience. Sorry for that.
Thank you very much, Wolfgang. No, I didn't want to interrupt you because again, you're giving a talk from Germany. The talk was really, really amazing. And so yeah, we went over time. So first of all, I would like to thank all the participants and feel free to, we don't have much time for official discussion. So I suggest we stop the recording here. But then of course, everyone is welcome to stick around for questions. We'll have as much time as Wolfgang has to discuss with him.